Now I introduce the importance of sampled policy search. This is part 2. Differential dynamic programming is an optimal control method. Now we use it as an important sampling method to provide the policy guiding samples for policy search. Usually, DDP includes 2 stages. One is a backward pass to generate a new control sequence, and a forward pass to generate a new anomaly trajectory. For robot system and linear quadratic policy, means the dynamic is linear, but the loss function is quadratic. So DDP optimizes a trajectory by alternating backward and forward passes. That's the idea of the DDP. Now, for example, we give a trajectory and its samples along the trajectory and define a difference. A differential, this is a very small difference. This is the state difference, and this is the action difference. Then the system dynamic and the real world are approximated as this system dynamic, linear, and this is the real world at the state S and action U. We use Taylor expansion to get this Taylor series. Here the R X, for U, and this Jacobian, and XX UU is Hessian. So now we see how can we use the DDP to generate guiding samples for policy search. First, we use the DDP recursively estimate Q function from the real world R and value and the state value function. Once we update, this Q value, then we can update the in the same way update the state value function and the policy terms. And then we have a deterministic optimal policy G is given in this formulation, this linear. That means from this state, we select the action U and this deterministic policy, and then we reach this Q value. So and so on, we generate samples. These samples are used as guiding samples for the policy for policy search. That's the idea. Because we use the DDP step by step, we improve the policy generator ideal trajectory. At the same time, we use this guiding samples to improve our policy. Finally, when we get a good trajectory generated by the deterministic policy G, and then we reach the final convergence policy, and which is the same as G. However, this G is a deterministic policy, but the policy we are searching is stochastic. So in the Markov division process, stochastic policy can be expressed in this formulation, because here is the state value function. Here is the action state value function. Policy is decide what's the action selected under the policy pi. So the pi can be expressed as the exponential formulation this way. So we can, if this policy we are searching is a Gaussian distribution over the trajectories, then the stochastic policy can be expressed as in this formulation. From here, first we use the policy G as the mean, and then we use this vector as the covariance. From the deterministic policy, then we can get the if our stochastic policy is in Gaussian distribution, then we can get from the G get static policy pi. Then how can we do it? If, for example, we have a C-term policy xt, which included the robot inside state and observation from the onboard camera. Of course, the camera, the observation feature point is extracted by using convolutional neural network and put together as the input of the policy network. Then we generate two outputs. One is for example, one is for the mean and one for the covariance. However, we just make sure we need the both number are positive, so we need exponential operation to get a positive number here. And then we use these two numbers, use the mean and the covariance. And because of the stochastic policy is a Gaussian distribution, then we get our final static policy we are searching for. For more details, please check with the reference. Thank you. Bye.